For this video, we are going to do one problem. It's a pretty nasty one though, so make sure that you've done a lot of practice before you do this problem. We're going to find the critical points, intervals of increasing, decreasing, relative extrema, intervals of a concavity, and the points of inflection for this equation. And this is a pretty nasty equation, so if this is your first example of doing this, pause and go do some easier ones in StudyForge or use the Khan Academy or Patrick JMT videos that are on the help site. This should not be the first time you try it, just because the equation is kind of icky. The process is the same, but this is a more complicated f of x function. Okay, so let's get started. Let's first talk about critical points, which means we need to find the first derivative, set it equal to 0, solve for x. So first derivative of this function, pretty straightforward. It's the power rule. Derivatives should be pretty quick at this point. Chapter 3 was about learning how to find the derivatives. Now you're going to use them. So power rule here, we take the exponent, bring it out to the front. We're going to multiply it by the coefficient, and then you have to subtract 1. And when you subtract 1 from a fraction, you have to make it a fraction. So instead of it looking like a 1, it's a 3 over 3. So 2/3 minus 3/3 is the negative 1/3. Same thing goes here. 5/3 comes down, gets multiplied to the 3, and then we subtract 1 from it, ends up being 2/3. So here's our first derivative equation. Let me clean it a little bit. Just cancel the 6 and the 3 and the 3 and the 3. And we end up with this, which is great. This is fine. But we need to solve for x. We need to set this equal to 0, solve it for x. This is not really the best way to make it look. So I'm going to put that negative exponent in the denominator and work on combining those fractions. That's the easiest way to solve this algebraically. So to do that, you need to combine the fractions with the common denominator. Common denominator in this case will just be x to the 1/3 power. So we can multiply the fraction on the right, top and bottom, by the x to the 1/3 power. And then just remember, when we're dealing with a situation where we're going to multiply those functions or expressions with the same base, we add the exponents. It's like this situation. There's 3 of them. That's why we add. So we're going to do 2/3 plus 1/3 here. Luckily, they already have a common denominator. So that's going to look like 5x. And it's, 2/3 and 1/3 make 3/3. Once you have your common denominator, we can just put it all together now. So now that we have our derivative equation, we need to find where it equals 0 and where it's undefined so we can get our critical points. So to find where it equals 0, that happens when the numerator equals 0. So we set 4 plus 5x equal to 0, solve for x. Subtract the 4, divide by 5. So that's our first critical point. Second critical point is where it's undefined, which means that would be where the denominator is 0 because you can't divide by 0. So our derivative is going to be undefined when x equals 0 as well. So we've got our 2 critical points. So check on this first part. Let's move on to the intervals of increasing and decreasing, because that happens when the first derivative is positive for increasing, when the first derivative is negative for decreasing. So it's helpful to set up a sign chart here. Put your critical points on the sign chart, it's just like a number line, and then you plug in numbers into the first derivative to figure out the sign of the first derivative. If you had the graph of the first derivative, you can just look at the y coordinates because that tells you the same thing. So we're going to pick a number less than negative 4/5. I picked -1, that would be like -5/5. And plug it in, we end up with a negative number on the top and a negative number on the bottom. So this becomes positive in this interval. And the second interval between -4/5 and 0, I picked -1/5. The reason I picked 1/5 instead of like 1/2 or something was because I wanted to do this math easy and cancel those 5s. So we end up with a negative in this case because the top is going to be a positive number and the bottom's a negative number. And then the next one, I'm going to pick 1. Nice easy one. Positive on the top, positive on the bottom. So that's a positive now. And you notice you don't really have to do the math. You can just look for it's a division problem. We're just looking to see if the top is positive and negative, and then decide if it's the whole thing is going to be positive or negative. The actual number doesn't really matter right now, just the sign. Okay, so this gives you the intervals of increasing and decreasing. If you're a calculus student, though, you really shouldn't just give us a sign chart, though. Like, you need to justify where the first derivative is positive or the first derivative is negative, and that's why it's increasing and decreasing because of the sign of the derivative. You shouldn't just stop at the sign chart. So let's recap what we've done so far so we can get to the extrema. First thing was we found the first derivative and then I simplified it so I can solve for x easier. We found the critical points by setting the numerator equal to 0 to find where it equals 0, denominator equal to 0 to find where it's undefined. Created that sign chart and plugged numbers into the derivative to find the sign of the derivative. And now this gives us the intervals of increasing and decreasing. And like I said, this probably, I did a bad job here. This isn't enough. The sign chart isn't enough. I should have put here f of x is increasing from negative infinity to negative 4/5 and 0 to infinity because the first derivative is positive. And then this one, because the first derivative is negative. I really should have put some more justification here. If you want all the points, you have to justify everything in words. Okay, so now let's talk about extrema. If you watched the previous video about analyzing the graph of the first derivative, we talked about, finding critical points on the graph of the derivative and then checking for the sign change on the first derivative. Well, here we can clearly see that the sign has changed. This is a critical point. The sign here is positive, which means there's a positive tangent line. The sign here is negative, which means there's a negative tangent line. The critical point means there's a flat horizontal tangent line. So there's a maximum right here. Same thing goes at x equals 0. It goes from negative, flat, to positive. So there's a minimum at x equals 0. So you look for the critical points, and then you determine if the sign has changed, the sign of the first derivative. And if so, you can say there's a maximum at negative 4/5 because that's a critical point, and the sign of the first derivative changes from positive to negative. And then there could have been, this is tricky now, at x equals 0, there could have been a relative minimum because it is a critical point, but because it was undefined, it's really not a relative extrema. It's actually most likely a sharp corner or an asymptote. So it has all the characteristics of being of an extrema, but you have to remember what we did at the beginning. We set the denominator equal to 0. The derivative does not exist there. There's something wrong at x equals 0, which means that the slope of the tangent line at x equals 0 is funky. So it's probably an asymptote or a sharp corner. So it does mean, though, that the graph of f of x changes from decreasing to increasing at that point. I mean, that could very well happen because that could be an asymptote. It could look like this, and then it could look something like this. Well, I don't know if that's the case, but anyway, that's the situation. So make sure you back up for a minute before you turn into a robot and just go without thinking. Think about what you've done. Go back to your critical points and verify that, yes, that was a critical point and it equaled 0, because if it's undefined, then it's not going to be relative extrema. So just be careful. Okay, let's move on to the concavity and points of inflection now. This means we need a second derivative. So remember, this was the equation for the first derivative after I simplified it. So if we take the derivative of this equation, we have to use the quotient rule, which is fine. There's nothing wrong with that. But I'm going to back up a little bit and use this equation for the derivative. If you remember, when I found the first derivative, I used the power rule. I used the bring the 2/3 down, multiply by 6, simplify, 5/3 down, and -1, simplify. And then I simplified a little bit. And then I ended up here, and then that's when I stuck the negative exponent in the denominator and then worked on combining the fractions. The reason I did that was because I was trying to solve for x, and that's how you do it algebraically. But honestly, to take the derivative of this one here, it's more complicated because you need the quotient rule. You have to simplify a little more, and I don't know, it's nothing wrong with it. I'm just going back to this one because I can use the power rule again. And that's just faster for me, I think. So we can use the power rule for this one. These are equivalent. If you go back up in the video, this is the expression I had for the first derivative before I simplified it and combined the fractions. Okay, so power rule, we bring down the 1/3, negative 1/3. We're going to have to minus 1 from this. That's going to look like 3/3. So negative 1/3 minus 3/3 is going to give us negative 4/3 here. And then we have 2/3 that's going to come down. We need to subtract 1. So that'll be negative 1/3 here. Let's clean this up a little bit. Multiply those fractions together. And now same thing, I need to solve this for x. Set it equal to 0, solve for x. So I'm going to do the same thing I did before and stick those negative exponents in the bottom and then work on combining a fraction or combining the two fractions. So in this case, they both have a 3 in common, so that's good. The x's, if you remember, we have to, we're going to multiply x to some power so we can get them to be the same. Remember, we had to add earlier. If you have this situation, I know I used that one earlier. So think about how we can add 1/3 plus 3/3 would give us 4/3. So we can multiply top and bottom by 3/3 here, or x to the 3/3 power. And that'll give us our 4/3. So we don't have to touch the left fraction at all and just tweak the right one. And you end up here. This will be 3x to the 4/3 power, and this is really just multiplying by x to the first power. So the top here is just 10x. And now that your common denominators are set, you can combine the numerators and do the same thing. We need to set this equal to 0. So it equals 0 when the numerator is 0. So we'll add 4, divide by 10. Oh, I'm sorry. This should be a 2/5. Let's change that real quick. Okay, there we go. Okay, so set the numerator equal to 0 to find when the second derivative equals 0, and we get x equals 2/5. Set the denominator equal to 0 so we can find when our function is undefined, our second derivative undefined. That occurs at x equals 0 as well. Those are possible points of inflection because remember, you have to verify that the sign of the second derivative changes at those points. So now we set up our sign chart. So same thing like we did for the first derivative. We're going to plug numbers in. I'm plugging in a number that's less than 0 here. Going to get a negative on the top. This is actually a positive on the bottom because you have negative 3 to the 4th power. That's a positive number, and then the cube root of that stays positive. So negative over a positive. And then let's pick a number between 0 and 2/5. I'm going to pick 1/5 just so I can cancel that 10 and 5. We're going to end up with a positive number here. And then pick a number bigger than 2/5. I'm going with 1. And we end up with another positive. Okay, so let's recap. We had our second derivative equation after I simplified, and our possible points of inflection at 0 and 2/5. And here's our sign chart. So there is a point of inflection at x equals 0 because that's where the second derivative is equal to 0, and the sign of the second derivative changes. However, x equals 2/5 is not a point of inflection because the sign of the second derivative does not change there. The graph of f of x will be concave down from negative infinity to 0 because the second derivative is negative there. And f of x will be concave up from 0 to 2/5 and then from 2/5 to infinity. Let's talk real quick about the second derivative test. So here's our first derivative equation, our critical points, and our second derivative equation. Remember, critical points are supposed to be where there's a horizontal tangent line, so possible maximum or minimum. So the second derivative test, what you do is you plug in the critical points into the second derivative to determine whether the critical point is a maximum or a minimum depending on the concavity. So if it's concave up or concave down, I said that backwards. This is the down, this is the up. It tells you if it's there's a horizontal tangent, and if it's concave down, then it's a maximum, or vice versa if it was a minimum. So let's do that. Let's plug in our critical points into the second derivative. This gives us a negative number. That means f of x is concave down at the critical point of negative 4/5. This causes a maximum at that point. When you plug in 0, however, notice what happens. It's undefined.